Welcome to the Math 134 Week 13 lecture. So this week we will discuss some applications of integrals. So the substitution method was something that was discussed earlier, and it works slightly different when you have the definite integral. So if you have a definite integral, we're going to discuss how to do substitution. We'll discuss the area between curves, and we'll discuss the average value of a function, sometimes talked about as the mean value theorem for integrals. Okay, so how does substitution work with definite integrals? So with the indefinite integral, we would take an integral, we would look at the integrand, and we would try to find a situation where our u, in this case g of x, has its derivative also appearing in the integrand. Okay, now the same concept applies for the definite integral. So the same idea, notice the integrand is exactly the same above and below, and the integrand for the integral in terms of u is the same above and below. The only difference is the a and the b have to change. So to find out the new a, the new lower limit, you plug it in to whatever you're substituting. So plug in x and find the u, and the u that results gets plugged in as g of a, and the same thing for g of b. Okay, so let's put this to practice. All right, so in this problem, the first thing that we have to do is decide what our u should be. So in this case, our u can be everything that's inside of the brackets, so 3 minus 5x, because if we take the derivative, we find our du, we get minus 5 dx. And the derivative of u is appearing in the integrand in the following sense, that the constants don't really matter, so all we need to look for is dx, and that's what we have. Okay, so this integral becomes the integral of everything inside the brackets became u, and u is being squared. And then dx is minus 5 underneath du. Now, one more thing that we need to do is make sure that the limits of integration change. So we're going to take 1 and we're going to plug it in for x to find out our u. So 5 times 1 is 5, and 3 minus 5 makes minus 2. And if we plug 2 in, we get minus 7. So we can go ahead and solve this new integral. So what we have is u raised to the 1 higher power, and we divide by that power, and the constants come along for the ride, which in this case is minus 5. So that denominator is simply just 5. So let's write in 5 there. Okay, and we want to evaluate this, the lower limit of minus 2 and an upper limit of minus 7. So our result is 1/5, we'll pull that out, and then inside of the brackets we get minus 1/7 plus 1/2, plugging in minus 7 and subtracting, plugging in minus 2. So all this boils down to 1/14. So notice that our answer is simply just a number. There was no need to do our back substitution to get things in terms of x, really because we're just looking for the area underneath this curve from 1 to 2, and that answer is directly 1/14. 1/14 is equal to all of these expressions above. Let's try another example. Okay, so this time we are evaluating an integral from 0 to 1. And again, our u value is where we want to start. So we want u to be 1 plus 7x, which makes du equal to 7 dx. So when we substitute in dx, we'll substitute dx equal to du divided by 7. So we're all ready to do our substitution. So this time when we plug in 0, we get 1. So we have an integral from 1 to the upper limit. When we plug in 1, we get 8. And we have a cubed root of u. And then dx becomes du over 1/7. So a 1/7 I'll pull outside. So I don't have to worry about that anymore. It's nice to pull the constants outside. So 1/7 just comes along. And now I can write u. It's currently to the power 1/3. So 1 higher power would be 4/3. And then multiplying by the reciprocal gives me 3 over 4. So I want to evaluate this from a lower limit of 1 and upper limit of 8. Okay, so plugging everything in, the constant out front would be 3 over 28, and then plugging in 8, I get 16, and plugging in 1, I get 1. So looking through the answers here, answer D is the correct one. Let's try another example. Okay, so now we're evaluating an integral from 1 to 4, and again we have to use substitution. So this time, my u should equal something that has its derivative appearing. So the square root of x is really x to the power 1/2, and that appears in this expression here, right? X to the power 1/2 is right here in that power. So that would make du equal to, bring the 1/2 down, and then x to the power of minus 1/2 dx. So if we write this as square roots, maybe this will look a little bit clearer on how to substitute things in. So x to the power 1/2 is the square root of x. And then if I multiply both sides by 2, I get 2 du. And then notice I have dx over top of the square root of x. So now I can substitute things in. So my new integral becomes the integral from 1. If I plug in 1, I get 1. And if I plug in 2, I take the square root of it. Or plug in 4, and I take the square root of it, I get 2. So now notice that e to the power of root x becomes e to the power u, and then everything else that's sitting here being dx over root x, dx over root x is 2 du. So I'm going to write 2 on the outside and then du. Okay, now we're all set up to solve our integral. So I'm going to write 2, just copying from above. The antiderivative of e to the power u is e to the power u, so nothing needs to be done there. And I want to evaluate that with a lower limit of 1 and an upper limit of 2. So if I plug in those values, I get 2 times e to the power 2 minus e to the power of 1. I don't have to write e to the power 1, but I did anyway. So looking through my answers, I can see that D is the correct one. All right, so hopefully that gives you a sample of how to do integrals that are definite by substitution. Our next thing that we're going to move on to is area between curves. So remember that the definite integral can find the area below the curve. So if you think about that, if we just get our maybe shaded green pen out here, if we can find the area underneath this curve, so underneath the red curve, and then we decide to subtract that with a signed area that's underneath the other curve going towards the x-axis, we would calculate all of that, and then we would also calculate all of this area here. So the integral itself, when we look at the area underneath the curve, can be used to find the area between the curves. Notice that the signed area idea here really helps us out, because this area here that is below the x-axis will actually be subtracted, and we will have a signed area here of a negative area underneath the curve. So if we're subtracting a negative area, we're actually adding that area. And then this part over here will be subtracted away. It'll be a positive amount subtracted with a positive signed area. So that part will go away, which really makes things work out quite nicely, so that, if we get our color coding out here again, let's say f of x, this is our top, you want to think about the top curve minus, in yellow, we'll think about that as the bottom curve, will give us the area between both of the curves. All right, so let's put this into practice. Let's see if we can do an example of this. So in this example, we have sine x and cos x, and we want to find the area between these two curves from 0 to pi. It's always nice, if possible, to draw a diagram, so let's do that. Okay, so the area that we're interested in calculating here is the area between these two curves. So if we shade this in, it would be this area right here until we hit this point pi over 4. Now when we hit pi over 4, both the curves evaluate to the same point, 1 over root 2, and then afterwards there's more area between the curves, and some of that is below the x-axis, and then it kind of gets cut off at pi in this fashion. Now when we write down our integral to represent the area, we're going to have to write this as two different integrals. So the calculation does include the absolute value, but in order to get rid of the absolute value, you need to decide which curve is on the top and the bottom, and that's why it's important that we evaluated it in this way. So first, our green curve is on the top, so first we do cos x minus sine x, our yellow curve, from 0 to pi over 4. And then secondly, we do the other section from pi over 4 to pi. So plus some more area from pi over 4 to pi, and this time around the yellow curve is the one that's on the top, so we need to do sine x minus the green curve, cos x. All right, so it's time to take the antiderivative. So antiderivative of cos is sine. Antiderivative of sine is minus cos, so we get to put plus cos and evaluate this with pi over 4 and 0, and then add all of that to our antiderivative of sine is minus cos, and our antiderivative of cos is sine, and there's a minus sign that we can factor out. And we can erase that plus sign there so it makes sense, and everything gets evaluated with a lower limit of pi over 4 and an upper limit of pi. Okay, so plugging everything in, plugging in pi over 4, we get 1 over root 2 plus 1 over root 2, and then we subtract, plugging in 0, where we get 1. And then the other term that's here, we'll write a minus sign and then an open bracket to put everything inside. We plug in pi, and we just get minus 1. And then we subtract, plugging in pi over 4. So this time we get minus 1 over root 2, minus 1 over root 2. And now if we put this all together, looks like we have a minus 1 that would cancel out with a minus minus 1. And then everything that's left is 4 times 1 over root 2. And if you like, you could write that as 2 root 2. So there's our final answer that represents the area that's between these two curves that's shaded in red on our page from 0 to pi. All right, let's take a peek at what we're supposed to do next. So again, we'll sketch the region between the curves and try to find the area. All right, so I'll draw my sketch up here. So my top curve looks like it's going to be e to the power x. So e to the power x will look something like that. So that is my y equal e to the power x. And then my lower curve is my regular parabola, but it's been bumped down by 1 unit. So it looks something like this. This is my y equals x squared minus 1. And then I have some vertical lines. One of them is at -1. So there's my x equal -1. And then another one is at +1, x equal to +1. And of course this area does get enclosed. This shaded red area here is what we're trying to calculate. How much area is there? And the integral will give us the answer. We just need to set it up and figure out what that answer is. So we have an integral that will represent the area, and that integral will be evaluated from -1 to 1, with our top curve being e to the power x minus our bottom curve, which is x squared minus 1, and I'll subtract a -1 to get +1. And we just need to take our antiderivative and figure this out. So antiderivative of e to the power x is e to the power x, and then x squared's antiderivative is x to the power 3 over 3, and then antiderivative of 1 is x. So we get to evaluate all of this from 1 and -1. Now if you like, you can do this term by term. So I'll do the e to the x term first. So plugging in 1 and subtracting, plugging in -1. So I get e to the power of 1 and then subtract e to the power of -1. So it looks like that. So that's the e part of it. And then I could factor out a -1/3 and then do the x cubed part of it. So plug in 1 and plug in -1. I would get 1 minus a -1, so that's 2. And then the x part of it, I'd plug in 1 and minus a -1, and I'd also get 2. And now if we notice that all of this stuff right here is +4/3, we can find that B is our correct answer. All right, let's take a look at what's next. All right, so we're supposed to sketch and find the area between the curves. All right, so my sketch this time around will look something like this, where we have y squared equal x, which is my parabola turned on its side, so the square root function. That is y squared equal x, and then we have the inverse of that function, the regular looking parabola, which looks like this. So that is my y equal x squared. All right, and we are searching for this shaded red area right there. So we'll go ahead and set up the integral. The integral is from 0 to 1 because these two curves intersect right there at 1. And then the top curve, this time, we'll have to solve for y. So we'll take a peek at this curve right here, and we will take the square root of both sides so that y equals the square root of x. And we don't have to worry about plus or minus the square root of x because we're only dealing with numbers from 0 to 1, which are positive real numbers. So our top curve is the square root of x, and we're subtracting away the bottom curve, which is x squared. Okay, so time to write down our antiderivatives. So x to the 1 higher power is 3 over 2 multiplied by the reciprocal is 2 over 3, and x to the 1 higher power is 3 multiplying by the reciprocal is 1 over 3, and evaluating from 1 to 0. 1 to 0 is kind of nice. When we plug in 0, everything goes away. And when we plug in 1, we just get the coefficients. So this is kind of nice. We have 2 over 3 minus 1/3, giving us 1/3 in total. All right, so we're on to our last application for the course, which is on the average value of a function. All right. So the average of an integrable function is given as follows. So I would like to draw a little picture for you of what's going on here. So if we have a graph let's say our function maybe starts down here and it does something and then it goes up here. The average value of this function is defined by taking the area that's underneath the curve and bunching that same amount of area into a rectangle. So let me show you what I mean. So if you say that maybe this value here is A, and over here we have B, and you want to take the area underneath the curve to start out with. So we'll draw some lines and we'll say, okay, this is my shaded area underneath the curve. Okay, if you were to take that very same area and say that we're going to take a rectangle that has the exact same width, so this width will be B minus A, that distance that I just drew down, and we're going to take some height that will have the exact same shaded red area. So the red area is equal to what was shaded underneath the curve. Well, there would be some height. Let's say that we call that height F average. So F sub av. Well, that is how we define the average height of our curve. So that line would be, something like, maybe like this line right here. That line would represent F average. And this makes sense because the area that's on the right-hand side, this area is equal to B minus A as the base of the rectangle multiplied by the height of the rectangle, which is F av. Now, if we take this equation and we divide both sides by B minus A, we would have the area divided by B minus A is equal to F av. And notice, finally, if we write the area as the area underneath the curve in the integral format, so the area is now written as the integral from a to b of f of x dx, we have our formula for f av. So the key is that the area underneath the curve is the same as the area that's bunched into the rectangle, or this area underneath f av is the same as the area underneath the curve. And as long as our function is continuous, this average will exist. That's simply the mean value theorem for integrals. Okay, so it might be nice to look at the different value theorems that we have, kind of collect them all together. Let's just draw a quick little picture of each one of them. So if I draw a function, our function has to be continuous. So maybe this is my function here. There's my f of x, and it's always from a range of a to b. So maybe there's my a and there's my b. And we'll collect in color coding each one of these theorems. So if you want to find a particular height, the intermediate value theorem says that that height exists. So maybe n is my particular height, and somewhere along the line there is a c where that height exists. Now if you want to find the slope by connecting the endpoints, that slope will also exist. So we connect the endpoints in a so-called secant line, then somewhere along the way that slope on the curve also exists. And then finally, the mean value theorem for integrals will be coded in yellow. It says that the average value of the function always exists. So, this f av line for a continuous function always exists. Okay, let's see if we can find some average values of functions. All right, so our job is to find g sub av. So the average value of g from 1 to 8. So the first thing that we do is we divide by 8 minus 1, multiplied by the integral from 1 to 8 of the function itself, which is x raised to the power 1/3, and we need to figure out what this number is. All right, so we have 1 over 7, and then x raised to the 1 higher power, 4 over 3, multiplied by the reciprocal, which is 3 over 4, and evaluating with 8 and 1. Okay, so this equals, copy all the numbers from above. We have 3 on the top and 28 on the bottom, and then plug in 8 and we get 16, plug in 1 and we get 1, so 16 minus 1 is 15, and then looking through the answers, 45 would be my 3 times 15. All right, let's take a peek at the next problem. So this time we want to find f_av. So f_av is equal to 1 over, because it's from 2 to 5, we would take 5 minus 2, the integral from 2 to 5, of x minus 3 all squared dx. So here I have 1/3, and then x minus 3 raised to the 1 higher power of 3 divide by 3 is my antiderivative, and I want to evaluate that from 2 to 5. Okay, and I always like to pull all of my constants outside so I don't have to look at them. So there's a 1/9 that gets pulled out, and then I just have to think about plugging in 5. So if I plug in 5, I would get 2 cubed, which is 8, and if I plug in 2, I would get minus 1 cubed, which is minus 1, so I have minus a minus 1. Altogether, I get 9 on the top and 9 on the bottom, so my f_av is 1. All right, one final problem for us to work on today. All right, this time we want f_av from 1 to 3. So we take 3 minus 1 in the denominator. This time I'll just write 1/2 directly. And the integral is from 1 to 3. And I want to take the integral of ln x to find my answer. Now, given the tools that we have in this course, we don't have the ability directly to find that antiderivative. This antiderivative is generally found by using a method called integration by parts. That's not in the course Math 134 at the University of Alberta, so we do need to give an extra hint in order to solve the problem. We need to give that general antiderivative, which is given as a hint. So we can just simply copy in that antiderivative. So the antiderivative is x ln x minus x. And notice that when we're doing definite integrals, we never have to write the plus c. So we evaluate this from 1 to 3, and we can plug everything in. So we get 1/2 on the outside. Plugging in 3, we have 3 ln 3 minus 3. And then plugging in 1, we get 0 minus 1. So it's minus a minus 1 or plus 1. And we can search out the correct answer here. So this time around, we have 3 over 2 ln 3. So I'm keying in on A as the correct answer. And if we combine the other numbers, we do indeed get minus 1. So that's the answer. And that's everything for this video. Thanks so much for watching to the end, and we'll see you on the next one.